Okay, we're looking at substituent effects. You have a substituent on the benzene ring and you go do an EAS reaction like bromination or nitration or sulfonation. Where's the new group going to go relative to the existing group? That's really directing effects. The other thing is, does the existing group make the ring more reactive compared to benzene or less reactive? That's really what we're looking at now, and there's going to be 4 groups. We looked at group 1 and 2, they were both activators. Group 1 is a stronger activator. What type of group would be group 1? What type of group would be a strong activator? Atom with a lone pair, but not a halogen. Okay, what would be a group 2? Most common is alkyl. It donates by induction, but not by resonance. Resonance is a stronger donation. You can also have some conjugated, like alkenes, pi bonds. Group 3, we'll pick up there. Group 3 and 4 are actually deactivators. Net. Many groups can donate and withdraw. The main question is, what's the net effect? Group 3, the net effect is withdrawing, and the most common in the group 3 are going to be your halogens. They're weak deactivators because they're weak withdrawers. They withdraw inductively. Chlorine is more electronegative than carbon. It withdraws inductively. But it can donate. It has a lone pair. It can donate by resonance. We can show resonance in the neutral molecule here. We can also show resonance if there's a carbocation. It could donate. Chlorine doesn't mind taking on plus. Oxygen doesn't mind taking on plus as long as it has an octet. That chlorine does have an octet. Chlorine can do both. But with the halogens, which is the predominant effect? Inductive withdrawal. So thus it is a net withdrawer. Because the inductive withdrawing is greater than the resonance donation. If this was an oxygen, the resonance donation is stronger with the oxygen, with nitrogen, sulfur, anything else. Some of this will be summed up at the end, so I'm not going to make miscellaneous comments right now. We're going to go through and just look at all the examples, and then we'll sum it up. Okay, group 4. Group 4 are strong deactivators because they strongly withdraw. Now with these guys, that's all they do is withdraw. They don't donate it anyway. These guys are going to have no lone pair, so they can't donate by resonance. They may have a pi bond, but they're not going to donate by resonance because it's not going to be a good resonance contributor. They only withdraw inductively. Actually, they can also withdraw by resonance. They only withdraw. How are you going to recognize these groups? These are going to be groups that have electron poor atoms with no lone pair. When I say atom, that's the atom bonded to the ring. Electron poor atom bonded to the ring with no lone pair. Because if it did have a lone pair, it would need to be group 1. The only other thing with a lone pair would be a halogen. That would be group 3. Okay, so it's not going to fit in here. Examples would be your nitro group. It is a strong deactivator withdrawer. What's bonded to the ring? Just nitrogen. Does that nitrogen have a lone pair? No. Is it electron poor? Yes, it has a positive charge. Other things. Your sulfones or sulfonic acids. The sulfur is electron poor and no lone pair. Electron poor because these oxygens. Most important in this group is probably your carbonyls. Carbon has no lone pair, and because of the dipole to the oxygen, it's electron poor. because it's electron poor, that carbon cannot donate inductively to the ring. They're nitriles, or cyano groups. No lone pair. It's electron poor because of that nitrogen. So all of these are electron poor. Positive plus, positive plus. That one's actually got a formal plus charge on it. It's clearly electron poor. All of these deactivate the ring significantly because of the withdrawing nature. And certainly a lack of donating nature. This is group 4. Let's review the different groups. 4 different groups are reviewed here. Group 1, 2, 3, and 4. Phenol is going to be the most reactive of these. Why? Because it has a lone pair, and the major effect of the oxygen, it can do both. It withdraws inductively, it donates by resonance, but what's the major effect here? Donate by resonance. Donator or withdrawer? Activator? Deactivator? Activator. How does it donate? Induction. There's no lone pair, but it does donate by induction. It's an sp3 carbon. Learned in Organic 1. Right? But inductive donation is not as strong as resonance donation. So it's a mild activator. Here's our line. Benzene would be right here. Bromobenzene. What's the net effect of the bromine? But it can donate by resonance because it has a lone pair. But the stronger effect is the inductive. This is the stronger effect. It's a net withdrawer. And so it's taking, net effect is to take electrons away from the ring, less likely to form a plus in the ring with your EAS mechanism. Bromobenzene is less reactive towards EAS reactions than benzene. If you get something like this, we don't know a common name for this. If that was an H, it would be benzoic acid. This is the methyl ester of benzoic acid. This is a group 4. It's an electron poor atom bonded to the ring. There's no donation possible at all. And it's a strong donation, withdrawing. Note the difference here. This is an ester, yeah? This is also an ester. This is strongly deactivated. What about this ester? That's an ester, right? O, carbonyl, argon. Is this strongly deactivated?
No.
How would you explain this one?
Resonance.
There's an atom bonded to the ring, and it's not a halogen.
Group 1?
Looks like group 1, doesn't it? It's strongly activated. The reason I put this up here because I think a while back I heard some students saying esters are always deactivators. Well, there's an ester and it's not a deactivator. You can't just broadly make statements. You have to look at structure, individual things that are going on. Answer this. Which one is more activated? The one on the bottom right or phenol? Someone said this one. Why is this one more activated than phenol?
More there.
I didn't hear it. Who picked the one on the bottom right? Why, Chelsea?
System,
Do what?
the pi system, there's p orbitals that interact throughout.
There may be. That may increase the stability. More stable compounds tend to be more reactive. More stable the compound, the more it just wants to sit on the sofa and not do anything. here's the answer. Which oxygen can donate more to the ring? This one or this one? We could say this donates to the ring, and we can maybe draw some resonance structures, but what is this one also busy doing? This one is also busy donating this way, pulling that oxygen. This group pulls the electrons this way, thus those electrons can't move into the ring as much. Here, these are ready to just move into the ring. Okay? While that's a strong activator, I put it in kind of quotation. It's not as strong as this one. And I think there's a chart from one of the books that sort of slips this one in somewhere maybe between these two. Okay? That's just trying to make an argument, and I would expect you guys to be able to make such an argument. Okay, I'll give you some relative actual numbers. Compared to benzene, what's the name of this compound here?
Anisole.
Anisole. If you nitrate anisole, using nitric acid, sulfuric acid, it nitrates 10,000 times faster than benzene. I'm sure that's probably rounded off. Right? That's a big number, 10,000 times faster, just because of the methoxy group donating into the ring its electrons. Stabilizing what? The sigma complex, which has a positive charge. We'll see more exact resonance structures a little bit later. Toluene with the methyl is only 25 times more reactive than benzene. So it is more reactive, but the methyl can't do resonance. It can only do that weaker inductive stabilization. If you try to nitrate nitrobenzene, that is put an additional nitro on, nitrobenzene is 100,000 times slower to react than benzene itself. Doesn't mean you can't do it. Because how do you make TNT? You nitrate, say it goes here. Once you put that on, the next nitro is going to be more difficult. We will look at multiple groups. That's an activator, this is a strong deactivator. And you put another one on. Now the ring becomes even more deactivated. Putting the third one on can become difficult, but it can be done. It requires longer and heating. What if the methyl wasn't there? Is it easier to make trinitrobenzene than trinitrotoluene? Or with the methyl there, does it help us? Yeah, that's one of the reasons the methyl is there. Because you can put 3 nitros on toluene relatively easy. But if you try to put 3 nitros on benzene, it's a touch more difficult. And you have to heat it pretty high. It's not good to heat these molecules high, because what will they do? Yeah, that's one of the reasons the methyl's there. Help put the nitros on. Actually, without the methyl, it's more explosive. That's more explosive. It's also more difficult to make. Okay, these effects are additive. Sort of what I just did here. Which one of these 4 is the most reactive towards an EAS reaction? You can just kind of sum these effects up qualitatively. Which one looks the most reactive? I see I'm going to call this an SA, strong activator. That makes sense? And what is this? How about a weak deactivator? Okay. What is this here? Weak deactivator. So which is more reactive? I mean, that's a wash, and this has got a strong activator. So that's not the answer. This is more reactive than that. Okay. What about this one? What type of group is this? Strong deactivator. Well, that's not going to be more reactive than this because this has an activator and only a weak deactivator. Does that make sense that that is no more reactive than this? How about this? We got a what? That's a mild. Hold on, instead of mild, over there I use weak. So let's call it a weak what? Activator. And this is a strong deactivator. Does this look more reactive than this? No. This is your most reactive. Now, we're up there. Now, what if I then compared that winner to maybe something like, and we're not going to talk about positioning yet. Oh, we're about positioning. Which is more reactive, the one we circled or this one over here?
No.
We got a strong activator and a what? Weak activator. Which is more active? Yeah. I mean, the amine in the OH is a wash. The methyl is a stronger activator than the chlorine, so this would be more reactive. Here's a table from an older book. The groups 1 through 4 are unique to me. Other books do it very differently. This book calls things what? Activating substituents. So all these are activating, but then they classify activating into strong, moderate, and weak. Now the strong and moderate is what I call group 1. And I labeled group 1 according to my groupings. Here's that O ester with the O bonded to the ring. So they call it moderately. These are my group 2, mainly the alkyl, but you also have some conjugated alkenes. Then we have down here the weakly deactivating. Group 3, halogens. That's the same as we said, right? Group 3, halogens. It's a good exercise to consider. Why is the iodine more deactivating than the fluorine? These are grouped in for the order. Anybody have a educated guess? Mark?
It's bigger, so you can like withdraw more electrons, something like
But fluorine's more electronegative. Withdrawal how?
that.
Induction? Induction is electronegativity differences. Fluorine's more electronegative, it should withdraw more inductively. Think about it. There may be a question in the workbook about it. The stronger, it says moderate deactivating. See, I kind of group these together. You can look at it. Basically, these are all sort of electron poor. Carbonyls, we said here. Interesting here, the big arrow that comes down. An amino group is an activator. Nitrogen with a lone pair, activator. But under acidic conditions, the amine will be protonated and it'll become NH3. What type of group is it now? Well, look at the, okay, it's a new group. We haven't memorized it. We have to look at it. It's a nitrogen with a positive charge. Does it have a lone pair?
No.
So it can't be group 1. What does a nitrogen with a positive charge look like? Looks to me like an electron poor atom. What group does it seem to be? Group 4. It's an electron poor atom with no lone pair. That's group 4. Protonation of amine turns it into a deactivating group. So if you're doing a reaction under strongly acidic conditions, you can't just say the amine is an activator because maybe it's protonated. So the effect can vary depending on your pH or something. Okay? So that's a pH dependency. Now on the far right, we see this idea of directing effects. And we're going to get to that next, and you can see the groupings. Look back at this at that point. Question about activating. Again, resonance structures will be important, and we'll look at those a little bit later when we summarize really all of this. The next effect is directing effects. For example, if we have anisole and we nitrate it with our standard nitration conditions, where's the nitro going to go? Because we have three different places. It could go ortho, and in fact you get 45% there. It could go para, 55. You only get a minuscule amount of meta. Because of this outcome, we say that the methoxy is directing the group ortho-para. Okay? Ortho-para director. As opposed to any meta. Ortho-para is your major products. Meta is either absent or very negligible. Maybe up to 5 or 10%, but it doesn't approach these. Now, we can make this statement here. Which groups are going to be ortho-para directors? And by the way, yes, you do get a mixture. Ortho and para. And you would have to separate these. Okay? We will, as we go along, we'll see how para is a little bit more favored. In fact, you see how much is the para favored? Really, how much is it favored? By what percent?
10%.
Somebody? You say Greg?
5.
You say 5 because, like voting, 2 people vote, it's only 1 person or something. Because if this was 5% less, it'd be 50, and you get 5% there, they'd both be 50? Okay. Depends on how you... Well, it's much greater than that. Because we really divide this 45 in half to make it 22.5% ortho, 55% para. Why do we really divide that in half? Because there's 2 ortho positions. So you got 2 ortho positions. Just because of that, it's twice as likely to go ortho. And if we had gotten twice as much, we would have said the reactivity is about the same. Well, we didn't even get twice as much. So really the para is giving more. A single position get 55, 2 positions only 45. Why do you get more para versus ortho? It's not an electronic effect, it's a steric effect. Because ortho, you've got to go right next to that group. So para is a little bit more favored, and in some reactions it's even more highly favored. But still for us, groups will either be ortho-para directors, and you get mixtures. Below we'll see groups that direct purely meta. Why? And how do you determine? Well, here you go. It's real easy. Groups 1 through 3 are ortho-para directors. Okay? Because any atom that can donate somehow will be an ortho-para director. Can a halogen donate? We donate by resonance. It's an ortho-para director. And we'll show why. Now, the halogen donation by resonance is not its main effect, but this doesn't say it has to be its main effect. What's the only group that does not donate? Group 4. Well, guess what? Group 4 are going to be meta-directors. And that's shown below. What type of group is nitro? Group 4. Okay? If you nitrate it, try to put another nitro on, you predominantly get which product? You get the meta product predominantly. And we say the nitro group is predominantly a meta director. Now you may get this is the actual outcome. 4% here would be kind of equal. 4% because there's two groups. Why is there a little bit more ortho? That doesn't make a lot of sense, but sometimes there's other reasons you can make an argument. It's still fairly minor. If you try to brominate the methyl ester of benzoic acid with bromine and like a little nail or something, iron tribromide made, you get the meta-bromo product. That's a major product. That's a group 4, right? Carbonyl. All carbonyls are group 4. If the carbonyls bind to the ring. Just one below. Another example. Take bromobenzene. We're going to iodinate it with iodine. We know we have to have an oxidant. Cupric chloride. We're looking to iodinate. Where's the iodine going to go? Ortho and para. Those are two predominant products. You're left with having to separate the two. This is the ortho-para director, right? It's 1 through 3, ortho-para director. In terms of reactivity, is this more reactive than benzene or less? Less reactive than benzene. So that's an activation effect versus a directing effect. Okay, let's look at a little bit of resonance structures to help illustrate the directing, also the activating. If you take toluene and you do an EAS reaction, reacting with electrophile, the electrophile can be added ortho, meta, or para. Top shows adding ortho. I really hate this here. To me, it means nothing. Okay? I don't know what that pi bond is supposed to be doing. I see apparently it's making the bond to E up here and plus here. I'd rather you say, hey, I'm going to pull the electrons away from the bottom carbon and leave it plus. So grab it, pull it away, hinge it up, and go attack. And it means something in your mind. Here's the pi bond. There's the electrophile over there. Here it is over there. Pi bond here. Apparently, since we're adding the E to the top carbon, the electrons are pulled away from the bottom carbon, they go attack, leaving the bottom carbon plus, right? Okay? You got to vision that. Just doing an arrow like this, not knowing what it means, no good, right? So I wish books would be a little bit more precise, and I expect you guys to know what an arrow means. Okay. From there, here's our sigma complex. We can do resonance structures. Windshield wiper over, plus here. Windshield wiper down, get plus there. Those are your 3 resonance structures. Is one of them particularly stable? Because of the methyl. We're looking at the effect of the methyl. Right here, yeah? Right here we have the methyl donating. This looks like a secondary with resonance, but what do we have here? Tertiary. Inductive of the methyl. There you go. That's the stabilizing effect. That really makes toluene more reactive than benzene. But we're also going to see the directing effects. Look if it goes para. I don't know what that means. It looks like a pi bond's attacking the electrophile, but I don't know which way to put the cation. Okay? I'm going to pull away from this and pull the hinge down and attack the E+, okay? Like this. Burn, leaving that as a plus. Resonance here, resonance there. But look back here. What do we got? We get this good resonance structure. Effect of the methyl. Let's do a meta attack. You need to figure this out. All right. We get this cation, hinge it over, cation, hinge it up, cation. Where's the good resonance structure showing the effect of the methyl? The plus never falls on the carbon with the methyl if you do a meta attack. This is your intermediate. it's not going to be stabilized like these other two pathways were. Because it's not stabilized, it's higher energy, the activation state leading to it is higher, you're going to get less of this pathway formed or operating. Which two pathways are favored? Ortho and para. Okay? Does this make sense of why ortho para is favored by the methyl being there? Let's look at a group with resonance. The resonance structure is the same on the previous page, except instead of a methyl there, you've got an NH2. So I'm not going to go through how we get to the resonance structure. It's the same thing. Boom, boom, boom. But here, we actually have additional resonance structures. Because something with a lone pair can donate by resonance. Here, instead of saying the amine donates by induction and stabilizes this like the tertiary, instead it donates by resonance, and we can actually draw an additional resonance structure. Note the nitrogen does take on a positive charge, but it's okay as long as the nitrogen or oxygen has an octet. And this is actually your major resonance structure because why? Very good, Gifty, because it has 4 or more pi bonds. More bonds. Resonance structure, okay? More bonds, better. It's your major resonance structure. You also get that major resonance structure down here. Plus falls there, resonance structure. But you do not get it when you do meta. Because the plus never falls on the carbon where the group is. Because you don't get that resonance structure, the meta is not stabilized. You get these two pathways predominating. In terms of activating, again, this is a much greater effect than just resonance, than reductive donation. So this really makes these pathways better than like toluene or benzene, resonance donation. Now if you have a nitro group or any other meta director or any other group 4, here we actually get something bad if we do ortho pair. If you do an ortho attack, you get plus, plus, plus. The plus will fall where the group is. But is this a good effect? You got a plus right next to a plus. That's actually a destabilizing effect. This is actually bad. You also get the bad one when you do para. Bad. Pluses next to each other. But if you do meta, the plus never falls where the group is, and so you don't get the bad. So the reason it goes meta is not because there's something good, it goes meta to avoid the bad. Okay, we can sum this up a little bit more. Your directing effects are also additive, just like your activating effects. But they are additive in different ways. In some cases, they may reinforce each other. In some cases, they may oppose each other. Here's an example. What do you want to call this compound? Paramethyl benzoic acid? What type of director is this? Ortho-para? What type of director is that? So the meta director is directing here. Meta. Where's this directing? Here and where? There. But the para position is blocked. Now there is unique chemistry where you can still do something there. But for us, typically, we're just going to say it's blocked. So, okay, this is blocked. So when you do an EAS, where do you predict the group is going to go? Ortho to the methyl, check. Meta to the carboxylic acid, check. This is reinforced directing. If you chlorinate it, chlorinated aluminum trichloride, you get this as a major product. Does that look like a reinforced direction? Okay. You can also, though, have opposing direction. And with opposing directions, you may have clear winners or you may have not so clear. What type of director is this ethyl? It's an alkyl, group 2, orthopara. Methoxy, group 1, orthopara. So this group directs where? Ortho, para, but para is blocked. This group directs where? Ortho, para, but para is blocked. So one group directs here, one group directs here. We're doing a sulfonation. Where does it go? Well, here's your answer. Your strongest electron donator wins out. You can either get the stabilization from this group or stabilization from that group. Well, the stabilization from this group is going to be better. Ortho stabilization. If you sulfonate, you'll get this as a major product. Which is the greater direct donator? Methoxy or donates by resonance, group 1. Donates only by induction, group 2. Stronger donator directs. So it went ortho to that. Down below, we have a not so clear winner. Both of these are ortho-para directors. This group directs here, this group directs here. Which one's going to win? They're both group 1. The OH is a little bit stronger. Why? If we were to make an argument, I would argue that this is a little bit stronger. Because when this takes on resonance, what charge develops on the oxygen? Positive? When you have a positive, how does the methyl affect the positive? I mean, if that's positive, is the methyl going to help it or hurt it? It'll help it. I mean, there's no methyl to help it here. Methyl's a donator. This oxygen is going to be able to take on more positive. So I'd say it's a stronger donator, we would say it directs there. But that's a finer kind of argument. In general, there's going to be probably 2 major products because there's not a clear winner. They're both group 1. Here you may indeed get 2 major products, where up there you may get only 1 major product. Here's another example. If you take this compound, brominate it, it's a meta-director, so it's directing where? Here and here, that's blocked, so that's directing here. Ortho-para, ortho, and para. So the chlorine is directing those 3 places. Which one should direct, based on what was stated? The strongest donator, which is which one? Chlorine. Yeah. So the chlorine's going to direct. We can get products where they're ortho to the chlorine, ortho to the chlorine, or para to the chlorine. All 3 are likely. Probably going to be a mixture you're going to have to somehow purify. If a company makes this compound, they're going to have to spend time purifying it, separating it, getting low yields. If you try to buy this product, it might be pretty expensive because the company had to deal with separating these mixtures. Is there one of these 3 that you could say might be less predominant? This one you could argue that, for the bromine to come in between the 2 groups, it may be a little bit hindered. This ortho position is more accessible than that ortho position because it's just steric congestion. So you may actually get fairly little of this because of sterics. What do you actually get? Well, that's, you have to go to the lab and do it, or look up in the literature, see someone who's done it before. Okay, predict the product down here. We'll do vanillin here in class. You can do the one below on your own. Anybody had any vanilla wafers lately? If you have, you've been eating that compound there. It tastes like vanilla. Don't tell anybody, but it ain't really vanilla. If you brominate it, what's the major product going to be?
Ortho to the oxygen methyl property.
Ortho to the phenol.
Ortho to the methoxy.
Here.
Yeah, I would say first.
Which group or groups are going to direct? Is this group going to direct, or the other ones? These are going to direct. They're stronger donators. This group donates, OH will call O, this group donates here, or here, or here. Those two are blocked. One of the orthos is blocked, one of the pairs is blocked. So this group donates here if it wins out. If this donates, it's going to donate here, here, or here. Well, that is something that is blocked. Of these two, can you make an argument for which one might be the ultimate?
Left.
Yeah, that one's between two groups. So we could say this group's going to donate para, or this group's going to donate ortho. Now at this point, we could say, well, this group might want to have a little say. Where's this group going to donate to? Well, X or O here? Yeah. So maybe let it actually win out when you got kind of a tie. And there, ortho to this group, but meta to that group. Yeah, this group doesn't really get to affect. If it did, we would go there, and it would go against two groups. So see how I did that? Kind of give a rationale. And indeed, if you brominate this, you indeed get as major product. That's indeed the major product, and we sometimes do that reaction on day 2. Haven't done it in a long time, but it's indeed your major product. You can do the one below on your own. Here we have two different rings. Asked to do a mononitration. First off, which ring is the nitro more likely to go into, be added to, and then what position? Let's look at the next handout. Now we're ready to go back to more EAS reactions. Again, what do we put on the ring? Halogen, nitro, sulfonic acid. What else do we put on the ring? That was really it, wasn't it? The nitro we saw how to reduce. Now we're going to start putting carbon on the ring. Top here got a little something there stretched out. Friedel Crafts, alkylation. Put alkyl groups on a ring. The electrophile, the E+, is just going to be a C+, a carbocation. We can make carbocations The ring will attack them just like an E+. Have we ever made carbocations? Made plenty of them in organic 1. We made plenty of them during test 1. So any way we've ever made a carbocation, you could conceivably generate one and have the ring attack. Here's an example. Benzene, isopropyl chloride. Aluminum trichloride is going to be a Lewis acid. We can get the isopropyl group on plus HCl. It's going to be very analogous to reacting chlorine with this to chlorination. Here, the chlorine complex with the Lewis acid. Same thing here. This complex is with the aluminum. We get AlCl3. That is now a minus. That's a plus. At that point, this chlorine would like to get some electrons back. It would either say, hey aluminum, give them back to me. You would go back here. On the other hand, it could say, hey carbon, I'm out of here. I'm taking my electrons with me. And if that ionized off, can a halogen just ionize off? Sure, we saw that in organic 1 lots of times. This is not just a halogen, a positive halogen. It really wants to ionize off and become neutral. If it does, what do you get? Carbocation plus AlCl4, the aluminum is minus over there. So here's how you can generate a carbocation from an alkyl halide. Now the benzene ring can attack. I'll pull away from the bottom. Attack here. What do we get? I pulled away from the bottom. It went and attacked the isopropyl, so we just made that bond. That's a plus, and we have pi bonds. Sigma complex, resonance stabilized. You should be able to draw resonance structures of this. From that point, what do we need to do to get our product? Just the same old thing. Something needs to take the H, restore the aromaticity. What can take the H?
Zero.
This aluminum can say, hey, I love you, CO, but you and your electrons need to go. Chlorine is like, okay, I'm out of here. My 2 electrons will go take the H. These electrons will move in. What does that give? We restored the aromaticity. We made HCl when this broke away and bonded to the H. And we reformed what? Yeah, it's not written over here. Plus AlCl3 reformed. Because it's reformed, it's a catalyst. And because it's reformed, you in theory only need a very small amount. This is called a Friedel-Crafts alkylation because we put an alkyl group on the ring. Secondary carbocation, those are reasonable, right? We'll pick up here next time. Please look ahead. After alkylation, we'll do acylation, which is where we put a acyl group on the ring. Everybody get 2 handouts today? The other one is multi-step synthesis. Please be taking a look.
We didn't get that.
They're tan, gray sheet. Somebody have the gray sheets?
What do you say about the beta and alpha thing?
The only thing that we know.
Wear it off a little bit.
I'm for the group that did that by accident. Oh wait, you were in my time.
Be patient.
It doesn't matter. Everybody's trying to walk in before they're done.
Yeah, well.
And then when we look at the structure, we see also matches what the activity is. That's why it's really group 1 to 3 is really determining where the substitution is going to go.
Well, the strongest node is direct. But, you learn like this.
Okay, I'll give it right back.
Strongest.
Yeah. See, just go down there.
As you go down, this donates to you. This donates to you. This does donate, but actually the withdrawal is the major factor.
You have it.
This doesn't donate at all.
Okay. All right, I got you. Thanks.